And this brings us up to the basically modern encryption systems. And the first, we will look at a number of examples as well, or a number of ciphers in the newer system, and we'll look at two of them. And the first one we'll look at is called DES. Okay, we look at DES cipher. DES is a block cipher, guys. It's a conventional encryption cipher, pretty much like Caesar's algorithm and all those, but obviously it's a more modern one. It's the first used electronic system cipher, and that was kind of globally used. And it was actually approved, used in the United States government. All documents sent from one government, from one department to any other department in the US government, it had to be encrypted using DES cipher. This is back in just before the turn of the century. And it was used for about 10 years before it was possible, or it became possible to break it within 13 hours using few computers working together. And that's when the American government decided, okay, it's no longer secure, let's call those experts again. And they went back to the standards organizations, and the standards organizations, they made it more secure. Anybody knows how to make an encryption system more secure? Any idea? Use longer key. So that's exactly what they did with this DES cipher. This DES cipher uses 64-bit key. They turned it into 128-bit key. So they used a longer key, and that way the system became more secure. But that's not enough. So you can, any other way?
Destroying the key.
Hold on. Use a more complex algorithm. And what do we mean by more complex algorithm? Something that we cannot solve? What's a more complex algorithm? It takes more time. So to encrypt one character, it'll take slightly longer time. So instead of half a second, it'll probably take a second. But they actually made it 3 times longer to take. So they increased the size of the key, they increased the complexity of the algorithm. The rest of the standard, the algorithm remained almost the same. And they called it, instead of DES, they called it triple DES. So the 3 times DES. So basically it's longer key and 3 times as complex. And they issued it, and it was used again. And it's probably, and then after maybe about another 10 years, that system was not also fast enough. It should maybe, I don't know, maybe one of you will design a system that it's not always fixed key. You can say, okay, I'm going to use some longer key and that's it. And it just becomes, you don't have to change the whole thing. But in those systems, it's based on the size of the key, all the algorithms, and you go to the bit, maybe the 50th bit based on that key. But anyway, so even triple DES became not secure enough. So they even made it even longer key, and more complex algorithm. They added more complexity to the algorithm, and they have it, and it's called the advanced DES, ADES, AES. And that's still in operation right now. It's kind of starting to run out. So it's still used in many locations, but it's probably towards the end of its life. So they'll have to increase it again, or they do something with it if they need to improve it. Or somebody else come up with slightly different system. So let's look at DES now. The key space refers to a set of possible permutations of a key, and if a key were 8 bits or 1 byte long, then the key space would consist of 2 to the point of 8 or to the power of 8. That's 256 possible keys. So if you have 1 byte, your keys are going to be a number between 1 and 256. But then every time you add 1 bit to the key, you're going to double the size of your keys. So by adding 1/9 bit, your key size, the range of your key is going to go to 512. You add 1 more bit, then the the key goes to 1024 and so on. So in DES, they actually use a 56-bit key. So it's 56-bit. And why 56-bit? They actually use 8 bytes, but 8 bytes are 64 bits. But in the older days, and still this is the practice today, parity. I don't know if you've heard of parity. Parity, checking for errors. And an extra bit at the end is called the parity bit. It just counts how many ones do you have in there. So if you store information, every time you pick a file and send it to the printer, the old operating systems, they check for parity. Even the new operating systems, they still do check. So parity system is an error detection system, really. So if you store information or you send somebody a message and they receive it, they check it for error, that nothing has changed. And if something has changed, then at least they tell you there's an error, don't read this message. Or if you store a file onto a hard disk and come back 3 months later and read it, operating systems automatically do that in the background. Most of the time there is no problem. But so you might get a parity problem. You get a warning, you have a parity problem. That means, some bit has changed. You don't know which one it is. Parity system is not a great system. It's a very poor system, in fact. It will only discover, it just counts how many ones in this byte. And if, for example, we had put even number, we always put an extra bit that's not part of the data. We look at the data and we add 1 or 0 to it all the time. And that's called the parity bit. And why do we add 1 or 0? To make sure that how many ones you have is always going to be an even number, for example, or an odd number, whatever we agree on. So it's an old system, one of the oldest systems for error detection. And it's the least efficient systems. And it's one of the systems that does not discover most of the errors, but it's still the most used one. Anybody knows why? Everybody's still using the parity system, despite it's not being a great system at discovering errors. It's because it's been there, it's the oldest, and it's been there entrenched and designed into every system. And it costs more money to take it out, so they say just leave it. Don't do us no harm. To take it out, it costs us more money, so leave it in. We won't depend on it. But it's doing error detection. Every time your laptop sends a file to a printer, error detection, parity check is done. Whether you use it or not, it will tell you. If there's an error, you get a little warning sign that says, hey, I have a parity error. Then you know one bit has changed. It doesn't tell you which bit. And sometimes there are bits that change and it doesn't discover them, so it's not really a great system. But in the old days, that's what happened. We had 8 bytes, but the last bit of every byte, they was used as the parity, as in the old days, and still used today. So in fact, even though they use 8 bytes, but only 56 of them are really part of the key. The last bit is not really part of the key. So, and usually they get rid of it immediately. So, and it's a block cipher, so this system will take, DES system will take a block, and the block in the DES system takes 8 bytes, 64 bits. So it takes, if you want to encrypt a file, you open the file, read 8 bytes, 64 bits. And it's a block cipher. That means you're going to deal with this block now, with these 64 bits. Start messing them, moving them around, substitute. It does substitution and transposition. So it changes the position and replaces them. And it does that 16 times with the key. And finishes with the block, it writes it to, for example, another file. Take the next 16 or the next 8 bytes, 64 bits, do the same thing, send them. So it's known as a block cipher, and it's transposition substitution cipher. So we will go through how does it actually transposition them and how does it actually do the substitution. And when it finishes, it kind of replaces the whole lot. The entire file is substituted or is encrypted. So it uses a group of SPs, that's substitution or substitution and permutations. The substitutions are replacements. The permutations, it just moves things around within the same block. So it's a group of SPs and it does that about 16 times on each block and finishes with each block separately. And some of the substitutions, they have something called an S box. We'll look at S boxes. And S boxes are what's known as substitution boxes. And it's a box that you give it a few input bits and it's fixed. It doesn't change. Any number of bits in any particular order, like 1, 0, 0, 1, it will move this bit into change the position of those, and whatever comes out is your substitution. And it's actually fixed in that system. And it actually reduces the size of the bits as well. So you give it, for example, if you give it 6 bits, it only gives you 4 bits. So it's substitution, but it also condenses the data. It does 2 things. It changes the positions, but it also reduces the size of the data. We'll look at how it does that. And the permutation, again, they had a few kind of fixed permutations, that if you have a data of certain number of bits, they just change in position, change in the position. And therefore, it doesn't get rid of them, but it just changed this bit here instead of whatever. For example, it's in location 22, it moves it to location number 4, and so on. So it just keeps changing the position. And they call this the permutations at the start and at the end. So we look at the exact permutation and the exact substitution, how the substitution boxes work. I give you a quick idea, and when we get to it, you should have the general idea now, but in DES there are a number of substitution boxes. For example, you have a number of substitution boxes, one next to the other. And for example, here's your data, whatever your data is. So every substitution box, there's substitution box 1, substitution box 2, 3, 4, I think, I can't remember now, maybe 8 of them. And the way it works, every box will take 6 bits and fed into the box and comes out 4 bits. And the box actually feeds it out based on a matrix. So every box here inside of it is like a table of 4 rows and 16 columns. This is how it works. The columns are numbered 0, 1, 2, 3 all the way to 15, and the rows are 0, 1, 2, and 3. And the box is full of numbers. They have numbers, and these numbers are fixed, like they don't change. They're always already known by the standard. Whatever the numbers are. This could be 2, I'm just throwing now any numbers here, 7, 3, 4, 1, 12, 11, whatever it is. And they're all less than 15 or less. And maybe 0 here, and 1 there, and 6 there, 2. Right, so the way it works, it actually gets the first 2, the first bit and the last bit. This is how it actually, every box, this is the way it does. It takes the first bit and the last bit, puts them together, and it says this is the row. And the bottom or the middle 4 bits, and calls them the columns. So this is the table inside the box here. So it goes to row 1, 0. Remember the rows are 0, 0, 0, 1, 1, 0, and 1, 1. That means 0, 1, 2, 3. So this goes to row 1, 0. Yeah, so this is row 1, 0. We'll go to row 1, 0. And it looks at the column. What column is this? This is column 0, 3, 3, 3, 0, 1, 1, 1, which is 7, number 7. So it goes 0, 1, 2, 3, 4, 5, 6, 7. There it is. So now we have the row and the column. Whatever your data is, this is based on the data. So the data is split into 6 bits each. Every 6 bits are fed into one box. The box takes this 6 bits, the next box takes the following 6 bits, and so on. And the box each box has a table. It looks at the first bit and the last bit and say that's the row in my table. And the middle 4 bits, the biggest number is going to be 1, 1, 1, 1, which is 15. So it's going to be one of these columns. So in this example, maybe 7. So it goes row 2, column 7, number 11. That's the one I'm going to write out. That's the output of this, whatever this sequence of bits. It's going to be written out in binary 11. What's 11 in binary? Anybody knows? It's 8 and 3, right? So that's 1, 1, 1, 0, 1, 1. So this input 1, 0, 1, 1, 1, 0 going into this box, 6 bits came out of 4 bits, 1, 0, 1, 1. And this is substitution. That's how a basic substitution box works in DES. So it does 2 things. It changes the value, gives you a different value, but it also condenses your value, reduces the size of the data. So, I don't know, for example, if you had 48 bits, for example, we're going to end up, that's 6 of those or 8 of those boxes taken 48 bits, they'll end up with 32 bits instead. So it reduces the data. And that's one of the operations that happen in DES encryption systems. So we go through the details of what happens next, each one in sequence, but this is the general idea. So there are 2 basic operations. One is called substitution, and it uses a number of substitution boxes, and the other one is permutation. And permutation is also based on a table. We'll see how the table works in a second. So there are a number of functionalities that you need in any encryption system. And one of the features you want in an encryption system is called confusion. And the other one is called diffusion. Diffusion is trying to diffuse the input and the password and make sure that they're hidden. You don't want somebody to say, okay, can you encrypt the letter A, and then they look and they see something that they can, now I know what happens when you encrypt the letter A. You don't want the outcome, the output, to be influenced somehow by the input in such a way that you can actually visualize it or can work out, attack that system. And that's by diffusing the actual input data and the key together in such a way that even if you give me a long list of the same characters and then the character B, there's no way of you knowing how or being able to extract any information from how the system works. That's diffusion. Confusion is trying to make sure that the key and the input data or the ciphertext information that's there, that's come out, and the key, there's no relationship between them. So those 2 here, being in an encryption system, you try to hide any relationship between your input data, output data, and the key used. Even if you had the system and even a few keys, you can buy the system and use it and then start testing it. Okay, I'm going to give this key and then give this key and see what effect does it have. You don't want, you want to hide that effect between the ciphered message and the key in such a way nobody can actually say, okay, show me that ciphered message. Well, I know there's a relationship between that ciphered message and the key, then this is the key. So you can't work out what the key is, or even if you knew the key, but obviously if you knew the key, you're okay, you're the owner. But there is no relationship. So if you come with a new encryption system and you send it to be checked, then check it. Does it provide confusion or not? If it does not provide confusion, that means a few simple tests we can do, we can actually find a relationship between the key we use. Okay, I give you a few keys, and based on the results, I can tell you, what the key is that can be used now once I can see the outcome. of the encryption system. So confusion of a system, of an encryption system that hides the relationship between the key and the ciphertext, while diffusion is trying to hide the relationship between the input and the output, or the plain text and the ciphertext. Now, it can be, if you're asked in an exam, it can kind of, I don't know, it can be, oh, which one is this, confusion or diffusion? But the way I try to remember it this way, confusion, it's associated with the key, just the pronunciation, confusion and key, they're kind of closer. So confusion hides the relation between the key and the ciphertext. The ciphertext is always there. And diffusion, then, it's a ciphertext, not with the key, with the input or with the plain text. So if you're asked what is the diffusion property, is for the encryption system to hide the relationship between ciphertext and plain text. And confusion is hiding the relationship between what? The key and the ciphertext. So easy once you know it, right? Right, there's some systems you can actually, outsmart them by having a message and say, right, encrypt this message, and then let me change one character in the message, the last character, and see what effect does it have. And then maybe if I can see one character change in the cipher message, then I say, okay, that's when I change the last character here, only that second character maybe in the cipher, so I know where the relationship between them. So that's one way of attacking systems. They say, okay, if you encrypt a system, or if you generate or design a new system, it should have an avalanche effect. And the avalanche effect, I mean, if somebody wants to kind of break it and say, all right, even if they have the system, they actually buy the system and they start testing it, they want to break it. If they change one character in the plain text message, they take a message, they encrypt it, you get the ciphered message. Now take the same message, change one character and encrypt it again. You should have a huge change, not just one character. Actually, you should have more than half of the message, the ciphered message, changed by just changing one character. That's called the avalanche effect. And that should also be, that's a good property to have in any encryption message. And DES has all those properties, by the way. And then the last thing is called the completeness property. Your message, if you give a message of, say, whatever it is, 64 bits or 64 words or whatever, or 100 words, and you encrypt it, encryption depends on every part of that message. If you change one word or one bit, it's not like some bits that, okay, even if you change, it's not going to have any effect on the final result. So the final result is going to be changed. That means your system, your output, your going to depend on every part of your input system. If you come up with a new system that the first 2 bytes don't matter, whether you change them or do it, the outcome is still the same, that means that's the completeness effect is not there. So these 4 properties are important. You need to know them, and that's one way of evaluating systems, whether they are good encryption systems or not, whether they have the diffusion, the confusion, the avalanche effect, and the completeness effect. So this started, in the up until that point, but in fact, up until a certain time, the only encryption systems that were there are either substitution or not confusion, either transposition or substitution. And this is the first time that somebody came up, Mr. Horst Fistel, is that he decided, okay, it's better to have a stronger system is to include both. So in any encryption system, and since then, any encryption system that came up, they decided to use both properties in it. So from DES onward, every system that was generated, it actually uses substitution and transposition at the same time. So in DES system, they use a key. And they always had this problem. How do we get a system that the same algorithm that we use is going to be the same for encryption, is going to be the same for decryption, and yet it's going to reverse the effect of the ciphering message. So they tried maybe a number of techniques that you're going to have the same encrypt, the same message, the same instructions to be done. Like if you're on a program, if you're encrypting, you're on the same program, the same process, and it will, the second time it will decrypt the message. So what they came up with is that you take a message, split it into two halves, and encrypt one half. Only encrypt, say, the right half. And then once you finish encrypting it, swap the two halves together, the left and the right, and keep on working on the right. So you're actually, each time you're only working on half of the block that we're doing. And in this way, by doing this 16 times, working on each half each time, it actually, they found that it works perfect. So you keep doing it, whether you're encrypting or decrypting, you don't have to change the actual code or the actual encryption technique or the steps. It actually gives out the final result. So this is the transposition that's used in some of the DES systems. It's fixed. It's almost hardwired based on the input that the data you get. For example, you have 32 bits, bytes or ones and zeros, 32 of them, and you are going to change them into another 32 bits, but do the transposition. So changing the position basically of every bit. So bit number 1 is moved to location 9, bit number 2 moved to wherever it did move, 16 or 17, and so on. So, and this is a fixed one. You'd think they'd probably done it based on the key or randomness or something like that, but in fact, all the transposition that's in DES and all the substitution are fixed. Either the electronic circuit or the outcome, you can actually predict it, but it's actually, at some point, the key is involved, and then whenever the key is involved, that's the one that actually changes things. So, in fact, if you need to program it, all you have to do is have an array, and you change the arrays, the locations based on fixed kind of whatever the standard actually defines. And these tables are all available at the standard. And we look at the exact tables. And they had another one. Remember when I said here, your data, as you're encrypting it, is going to shrink smaller, because that's what the transposition or the substitution box does. See, SB stands for substitution box. So if you have a number of boxes and you feed the data, 2 bits are going to be disappearing, and you come up, you get something different, but you're going to get something smaller. So at some stage, you need to re-expand your data, because the input is a block and the output is exactly the same. The starting, like if you take 8 bytes, for example, or 56 bits to encrypt, the outcome is going to be exactly the same. So if you take 8 bytes, they're going to be, as input, they're going to be encrypted with 8 bytes. Even though at some stage they're going to be shrunk a little bit, condensed the code, and here there are functions that will expand the data. So the expanding the data, again, if you have an array of bits, and for example, in the top one here, as income, you have 32 bits, you end up with 48 bits. So you can also expand the bits. And there it is, bit number 1, which is moved to 2. So this is a transposition or permutation, but also expansion as well. So it does 2 functions. So sometimes you have permutation table, and sometimes you have permutation expansion table. So this is the basic stuff, and still pretty much the same idea with the triple DES and with the advanced DES. So this is a fixed kind of transformation of bits. And some of the bits, just in order to expand it, as you can see, bit number 8 is actually fed into 2 locations, One is number 11, I think, and one is number 13. So some of the bits are duplicated in order to expand. Now let me go and get the actual DES. Great one for implementing, if somebody is interested in implementing the actual DES. This kind of explains it in more details and give you an example and tries to work it out bit by bit. But what I'm interested in is actually showing the sequence of what happens actually to encrypt the data or to encrypt the information. It gives some standard introduction first about the information, when it started and how it got there, but I'll go straight into how to encrypt a message. And in order to encrypt a message, okay, in general, you take the message 64 bits and it's split into two halves, and you operate on one of the halves and then swap, operate one of the halves, swap, and you do that 16 times. Now, you also need a key, and it takes the key. The key is also 64-bit key, which we said one of the bits does not belong to the key, so in fact it's 56-bit key, but they call this a 64 encryption system, 64-bit, because the data is actually 64, and the key is, we can say, starts as 64 bits. But then what it does in DES, they create sub-keys. So out of the key that you supply, they split it into two halves and they start playing with the bits, and they generate 16 smaller keys. And these are the keys that are used for encryption. So you supply a key, and it's that out of that key, we extract 16 keys. So we look at the two steps, the two processes, how to generate 16 keys out of the main key, and then how to actually encrypt each time and which key you take. I mean, basically there is a loop 16 times, and each time it uses one of those keys that were generated. So when it starts first, it takes the message, whatever the message is, and turns it into binary. It looks at it as binary. It takes 8 of those bits and splits them into two halves, left and right half. But let me go straight to where the actual message starts. There are a few simple keys or data to use for testing purposes. This is the key that they suggest to use, if this was the key. And the basic idea, again, is similar to every other semantic encryption system. You need a key and you need the plain text message. In this now in DES is going to be 64 bits here and 64-bit key. They go in together. The key out of the 64 will create 16 sub-keys, smaller keys. And out of the message, we split it into two halves, and we perform on one of the halves using one of the keys. Go back again and perform on one of the half, the second key, third key. So we do this 16 times, and each time we use one of the sub-keys. So we look at the more detailed operation. So this is the message. Whatever the message is, it's converted into, in this case, hexadecimal, but we look at it as a binary. It's easier for us to look at it as binary. And we take the key and we generate the 16 sub-keys out of it. So we're going to go through the first operation. So this is the original message, and it's split into two halves, left and right half. It doesn't matter what the message is, but we're looking at the binary bits. in it. But it takes, you know, it's going to go through a loop 16 times, and each time it's going to use one of those keys. So we go through the creation of those keys first. Let me see if there is a general diagram just to describe the idea. There it is. Okay, this is what's going to happen now. This is what we're going to go through. We're going to take a key of 64 bits. We're going to take a message of 64 bits. First, we take that key and we pass it through a permutation matrix. So just basically, we're going to take the key and mix the bits in it. And also, we're going to condense it a little bit. We're going to get rid of the parity bits because they're not really part of a key. So we're going to get 64 bits and we're going to filter them out, get the 8th bit, every 8th bit gets rid of it and reduce the key to 56 bits. And in the meantime, we mix it up. So that's going to happen. First thing we'll do with the key. But this describes the entire process. And we'll look at the two separate parts. But we start with the key, reduce it in size, and permutate it. Anytime you see P is for permutations, C for condensing, so it's reducing in size. Now we split the key into two halves. So we started with 64, first reduced it to 56. Now we're going to split it into two halves. Whatever, what's half 56? Like 28 or something like that. So we get there. So we have the same key, but in bits. Split them into 2 bits, and we're going to shift each bit, each half is shifted to the left. Bits or 3 bits, we'll see later on. But it's shifted, let's just say 1 bit. So the entire key on the right is shifted one bit. So that bit is left. I don't know whether it's circular, I can't remember now at this stage. And then also the left one is shifted to the left. I think with the bit we move it from the left to the right. So both sides are shifted 1 bit, okay? And then we join them, and we join the key together, and we pass it through another permutation condensation matrix, number 2. So, right, we started with 64 bit, reduced it to 56, we split them into 2 halves, 28 each, move them, shift them a little bit, that means we change the key, the values, the numbers. Circular shift, join the key again, and we reduce it in size, and that's our first key. Right, so our first key is reduced again from whatever it was. We only do this once, reduced 56. Now we are working with 56. Split it into 2 halves, shift them, join them. That's the first key. And then we go back again, shift the 2 halves, we keep the 2 halves separate, shift them, join them. That's key number 2. Then shift them and join them. And that's key number 3. So you have a key, split it into 2 halves, shift them to the left, circular left. So you're basically rotating the bits. And every time you join them, and that's key number 1, key number 2, 3, you do that 16 times. So that's how we actually generate the 16 keys, a total of 48 bits in each sub key. So it's reduced from 64 to 56, and then when we pass the second condensation, it's reduced from 56 to 48, and every sub key is 48. So we're going to have 16 of those keys. That's what happens. So we're going to be doing something 16 times, and each time we're going to use one of those sub keys. Now you know briefly how those sub keys are generated. From the master original key, clear it, the parity bits, split it into 2 halves, and each half is shifted, join them, reduce it in size. That's your first key. Now, we forget about this. We still have the same 2 halves unchanged. Shift them again to the left, keep rotating them, and we get a different key each time. And these are the 16 different keys. So that's what we will actually go through now. Once you get the kind of the overall plan, then you can probably follow the more detailed one. So in that algorithm, we're going to create those 16 subkeys and encode each block 16 times with those keys. And even the data, when we get the data, we split it into 2 halves, and we only operate in one of the halves with one of the subkeys. and swap them around. So to create this 16 keys, we say we go through the first permutation condensation that gets rid of the parity bits. And then we split the key into two, left and right. We shift them to one side and join them, and that will give us the first key. Now, this is the first permutation table according to the protocol. The actual standard has this table in it. That's how you actually permutate the actual key, and that's how you reduce it in size. So they have, for example, you have the array of the key. You have a key of 64 bits. First thing, it says here, into this array or this table, bring bit number 57, location 57. Let's say you have the key from 0 to 64. Go bring number 57 here. This is bit 49, 41, 33, 25, 17, and so on. So it just basically, it's like you have an array, another array, bring them into the different locations. And this is the standard location. And it's easy to program, but it's nothing intelligent about programming it. You're just moving data from one array to another array, but in different locations. Based on a table, you don't have an algorithm or a function that calculates where to put that bit. So this is mapped based on this table. That's the designers, they said this is the way it should be done. And as you can see here, there's some bits missing. They wrote bit number 1, wherever bit 1 is, and number 2 is there, and 3 is there, and 4 and 5 and 6, but there's one bit, you won't see it. Anybody knows which bits are missing? The parity bits. What numbers are the parity bits? 8, 16, 24, 32, every 8th bit is missing off the thing. So that's the reduction, that's the condensation in size. So bit number 8 is missing. We did not use it, we forgot all about it. So now we ended up with 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 56 numbers. So we started with 64 bits, we ended up with 56 bits. And the missing ones are the parity bits, bit number 8, 16, 24, 32, and so on. So it's very simple and basic. In fact, it's so primitive, the way to program it. It's nothing intelligent about it, but that's the way it is. So, and this is, if you just want to visualize it, which bit went where, right? And it's basically says, you can see a bit 8 is not used at all. Bit 16 was not used. So it just tells you where to put each bit. If somebody's interested in programming it, this will be kind of a nice way to follow it. And this is, imagine this is the key we started with. Okay, it's not too important for us now, but if somebody was actually writing a code for it and they want to check, that's the key you start with in binary if you want to print it out. And then we got rid of bit number 8. That's 1, 2, 3, 4, 5, 6, 7, 8. That bit is gone. So wherever that bit is. Oh yeah, but we did permutation as well. So it went into a different location, but there are six of those bits. If you count the number of ones here and there, there'll be whatever bits, if you knew which bits, number 8, 16, and all that, they're gone, they're missing. So the next thing after that, so that's the first step, reduce the size, get rid of the parity bits. The second step, split it into 2 halves. We split the key into 2 halves. So remember, we reduce it from 64 to 56. Now we have those 2 here, 56, split them into 2 halves, 28 parts each. And we're gonna shift each half to the left and join them, and that's the first key. Then shift the same halves to the, again, and join them. And so the left shift, do a left shift and join them to produce the first number. And okay, we went through this, so this general idea. This is the shift. How many bits do you shift to the left? Remember, you have 28 keys, 2 halves. You're going to shift them. how many bits do you shift into the left? They say in your first loop, you shift them once. In the second loop, once. In the third loop, you do two shifts, or shift 2 bits to the left. 2 bits, 1, 2. I don't know why they decide to do this. Maybe to put a bit of randomness into it. It's not much of a randomness, but it actually worked. So this just tells you how many bits do you shift to the left. So let's follow here's the example. These are the 2 halves we started with. This is, say, the left half, and that's the right half. So both of them are shifted to the left once. So this one, they had 4 ones here. That one is moved to that side. So instead of 4 ones here, they're going to be 5 ones. So that's the next step. So that one there went to the other side. And instead of 4 ones here, it's 3. And now join these 2 together, and that's your first key. Then the second key, you keep shifting this. So instead of 3 ones to the left, you shift 1 more, so there's 2 ones left, and the other one goes to the other side. Same with the bottom half. So each half, you shift them to the left 1 bit or 2 bits, based on whatever the protocol is. And this is actually the actual exact keys that got generated, or the actual halves of the keys. Now, the sub-key formation, each time we do a shift and join, or merge together, then we pass them, each pair has 56 bits, and they're passed through another PC permutation condensation table. So it's reduced. So the key, we join the 2 halves together, and they're 56 bits, but we pass them through this permutation, so we mix the bits, but we also further reduce the key, and now we end up with a key that's 48 bits key. So even though we started with 64-bit key, every sub-key is 48 bits long. And this is the actual, if you want to see where each bit has gone to, that table actually defines these. This is another way of representing it. So again, they missed bit number 9 and bit 18 and bit 25, so they got rid of some more bits of the key. So this actually shows us each of the keys that were generated. First key, second, 8 keys, 16 keys. Of course, you don't have to, visualize or remember any of this. All you need to know is the general steps. If you're asked, how does it work? You say, okay, first, the key has to be, you take the key, we have to generate 16 sub-keys out of it. What's the sequence, or what's the steps involved in generating the key? You're gonna get rid of the parity, so you're gonna reduce its size, and then you're gonna split it into 2 halves, shift and join, that's first key, shift and join each of the halves, and you generate 16 keys. So, and that's the end of the 16 keys. Now, how do we still have time? Falling asleep? No. We have to get rid of it. It's probably the most boring part of the course, but hey, you need to know it, because it's actually DES is the basic. It's the foundation for so many other encryption systems. It pretty much follows the same ideas and the same. And as you can see with encryption, there's nothing strange or nothing, any difficult. It's just they need you to do so many operations that will take a bit of time if you knew the key. And if you didn't know the key, it'll take you years to finish. But in case of DES, after 10 years, it wasn't, slow enough to take. They were actually being able to reduce it to 13 hours. And that's when the first time they realized it wasn't a secure system. Okay, so how are we going to encrypt the message? Right. Encryption, again, has another general plan. I'll show it to you. But first thing we do with the message, they call this the initial permutation. As you can, the from the word permutation, you're going to take the message and permute it or to do a transposition. Just mix the bits around. That's the first thing we do. And this is the exact table in the protocol that says how to mix it. So you're going to bring bit number 58, make it bit number 1, bit number 50, put it here as number 2, the second bit to bring it into location 8, and so on. So this is the actual permutation. Does this make the message increase the size of the message or reduce the size of the message? No, there's no condensation, there's no expansion. You just take the message, mix it. Right. So this is again, if somebody was coding, that would be the original message. And that's actually after implementing that permutation, that's what you should end up with if somebody wants to test it and make sure that they're doing it the right way. This is visualizing where each bit has actually gone to if somebody needs to look at it. Now, we split the message, remember, into 2 halves, left half and right half. We're going to operate in one of the halves. But this is from now on, we're going to do this 16 times. Perform the operation on one of the halves. We're using one of the keys. We go into the second loop. We do the same thing. We swap the 2 halves and we operate on the other half using the next key, and so on. We do this 16 times. So from now on, this is what we're going to do. Split the message into 2 halves. This is the message after permutating. So first thing, we do initial permutation. And then we split the message into 2 halves. And we're going to start repeating this 16 times. We're going to look at one of the times. So this is the actual, well, putting it simply. We take the new left half is going to be the previous right half. This is where we're going to swap it. The previous right half is going to be a left. And we only operate on one of them. And the new right, we operate on the left. We take the left and we XOR it with the right half and operate it upon with the key. This is where we take the key, perform the operation that we'll do on the right half. Once we finish, XOR it with the left half and go back again to the start again. Swap the 2 halves and do the same thing. So it's basically our operation is going to be on the right half and using the sub key. And we see what that function is. That function there, that's the actual encryption function. So we encrypt the right half each time using one of the sub keys. We finish, we swap the 2 halves, and we still operate on the next right half. So we always swap left and right halves. We always operate on the right half. So this is what it looks like. It's just, you get the general plan. You get the message. This is not generating the keys. We've seen how keys are generated. They're simple enough. Now, this is what we do with the actual message, how it's encrypted. Take a 64-bit message, we mix it up. So permutation. And that's fixed permutation. Then we split it into 2 halves, the left half and the right half. The right half is performed, that's the one that gets encrypted. And there's a key that goes in there, the first key, second key, sub keys. And once we encrypt it, we XOR it with the right half, and then we swap the 2 halves and we do the same operation. We keep repeating this 16 times. After the 16th loop, then we do a final permutation. So we have an initial permutation, we have a final permutation. And it's an inverse permutation. And that actually, whether we are encrypting, it will generate something. Whether we decrypting, we do the same thing, and it will actually bring back the original message. So intelligent, this is probably the only intelligent part about the system, about this system. Actually performing the same steps in the same order on the same message or on the ciphered message, and it will bring back the original message. So just remember the general plan. We take the message that we want to encrypt or decrypt. But let's say the one now who talks just simply, keep it simple. We take the plain message, mix it, that's first permutation. Split it into 2 halves. Take the first sub key, perform in the right half. The result of that is XORed with the left half, and then swap the 2 halves. do this again, the same loop again with this key, second key, third key, fourth key, 16 times. When we finish those 16 operations, we're going to do the inverse of that function, the permutation. Like if you took bit number 2 or 68, brought it in, or 58 into number 2, you know we go on this one, go to number 2, put it in 68. The very inverse of that permutation. So the result of the final block, if you got the last function, you finished, this is the last block, the 16th left block and the 16th right block, you join them together and you do a permutation onto them. But let me go a little bit closer to the function. Okay, so this is the final permutation. You XOR them. But right through the function, remember we said there's the function here that performed in one of the halves. This is really the heart of the DES encryption system. DES encryption system has those substitution boxes. Remember I mentioned substitution boxes earlier on. It has 8 substitution boxes. And these functions, those boxes are really the ones that will encrypt based, like without, they don't even have the key as being input in there. But whatever they have half the data, that's 48, and they put it through these boxes and they come out as a 32-bit. So each time we reduce them in size, but before we put them in the boxes again, they are actually, they're expanded to 48. So once they're expanded to 48, every S box will take 8 of the bits and will generate, 6 of the bits will generate 4 of the bits. So these boxes, they reduce the size of the data as well as substituting. And this is the substitution part in DES. So let me go to an example of a box. Here's an example of box number 1. This is substitution box number 1 according to the, okay, so this is one of the 8 boxes. Each box has a separate table according to the protocol. So this is the actual box number 1, substitution box number 1. It doesn't have obviously the top row here or this here, but I've added those to indicate the number of columns and the number of rows. All right, I'll give you a quick example and give me the output as a result. This is S box number 6. This is the question for you, if you're leaving now. 1 0 0 0 0 1. Can you see this? So this is the input. These are, see, every box will take 6 bits as input, those 6 bits, 1 0 0 0 0 1, and will produce a 4-bit. Now, the first bit and the last bit represent the row bit, and that bit represent the row, and those bits in the middle represent the column in this table, in this box. And wherever they intersect, that value comes out as the output instead of this input. So what output will come out of this? This is row 1 1. Where is row 1 1 here in this table, in this S box? That's row 0 0 0 0 1 1 0 1 1. That's row number 3. 0 1 2 3. So this box here, this input, see, the input will decide, what value will come out at the same S box. So 1 1, you must take the first bit and the last bit, and they tell you which row. And the middle, 0 0 0 0, they indicate which column. Which column is column number 0 0 0 0. Right? Column number 15 is this one here, which is 1 1 1 1. This is column 0 1 2 3 4 5 in decimal, but the numbers are written here in binary. So the first column, let me change this for you just to make it more interesting. Which column is this? Now you have to tell me what value comes out of this. Oh no, I have a volunteer. Right, which row and which column? Well, you have to extract the row out of this number. This is the input data. Take the first bit and the last bit, and that tells you the row. So the row is that one and that one, which is row 1, 1. And this is the column 0, 0, 1, 1. Is, what's that in decimal? 3. It's number 3. So it's, and this one is also 3. So it's row number 3, that's 0, 1, 2, 3. And also row number 3, 0, 1, 2, 3. And they meet down here at number 12. And that's the outcome that will come out. And it has to be in 4 bits. So you need to be able, you need to know how to convert the number, how to write number 12 in binary. Do you know? What's 12 in binary? That's 8 and 4, I guess. 0, 0, 1, 1.
1, 1, 1, 1, 0, 0.
I was just testing. Okay. Now, if you want to leave, you'll have to get me the next one. Correct. It's your turn. You want to go? Okay, who? What's the output for this? Which row? Row what?
1, 0.
1, 0. Perfect. Where is row 1, 0? That's 0, 0, 0, 1, 1, 0. And which column? Which column? The middle, 4. So that's a number, what's that in binary? That's 1, 1, 0, 0. 12. So that's 0, 1, 2, 3, 4, 5, 6. So that's 0, 0, row number 1, 0, 1, 0, which is just here, and number 12, which is there. Okay. Now, if you want to leave, you'll have to get me the next one. Correct. The output has to be 4 bits. Sorry.